The electrophilic aromatic nitration reaction is pretty cool. You take benzene or another aromatic substance of your choosing, and you mix these with two of the strongest acids we have in chemistry, nitric acid and sulfuric acid. And from this chemical reaction, you form nitrobenzene. As I showed in the section 19.1 video, the nitro group looks like this. Okay, so that's the nitro group. Okay, nitromethane is used in drag racing. It's highly energetic. Trinitrotoluene is TNT. You may have experienced that in Minecraft, in video games, virtually, I hope, only of course, but that's made from toluene and nitric acid and sulfuric acid to make TNT. Okay, so here we are with the curved arrow reaction mechanism. Okay, so as I mentioned, the first step is always going to be this weird way to create the electrophile. Okay. And so what we have is nitric acid and sulfuric acid. So sulfuric acid has this Lewis structure here. And nitric acid has this Lewis structure here. And you can see why most of the time I just abbreviate sulfuric acid as H+, but we have two acids, so you'll get in trouble if you abbreviate both of them H+. So what you want to do here is protonate nitric acid. I mean, there's an argument here about which acid is stronger and so on, but what we want to do to get the correct reaction products is to protonate this oxygen atom right here, okay? And what this forms is, this is just an acid-base reaction here. We're protonating the nitric acid, and what you get from this is a super acidic nitric acid molecule. Okay, in this intermediate here, we want to kick off water, and that's generally a good thing to remember is that water is a good leaving group here. And so the lone pairs here on oxygen are going to kick off water here. And so in that step, you're going to form this kind of creature here. Okay. And this guy right here is called the nitronium ion. You won't need to memorize that, I don't think, but it has such a cool name. I just like to mention it. I always write it on the board when I make it. So that right there is E+. Okay, definitely it's positive. It's an electrophile, and when things attach or attack it, they attack the nitrogen atom, which is a little bit counterintuitive. So we'll see in the next step. If you have a nucleophile, it actually wants to attack here, and then the lone pairs go here. The lone pairs actually don't go towards the positive charge, which is somewhat interesting to me. A student asked me, why doesn't it do it the other way? And I didn't have a good answer for it. All I know is it doesn't make the right product. So we want to do this mechanism in the next step, all right? So now that we have the nitronium ion, let's use our basic boring benzene ring here as an example. Once again, I will draw in this hydrogen here. Let's keep track of that. And let's go ahead and draw in our nitronium ion here. Okay, put the positive charge on the nitrogen atom. And when the pi electrons here attack, remember to attack the nitrogen and kick the electrons out towards the oxygen. Now when this happens, so we call this the attack step. Benzene is attacking our electrophile. We form this intermediate here. And it looks very weird if you haven't drawn these Lewis structures and looked at things for a while. But this right here is called the nitro group. We're going to abbreviate it as NO2 in the next steps, okay? Let's draw in that nice little hydrogen there, okay? Now in this chemical reaction, we have sulfuric acid, we have nitric acid. Any one of those oxygen atoms in any one of those two acids can be used to deprotonate this hydrogen in the next step, okay? So in the next step we have, so this is attack, and then we have deprotonation. So here I'm just being lazy and writing NO2, okay, which is perfectly acceptable. And we're going to have to create some kind of base or something that's going to deprotonate. So I could use nitric acid, or I could use sulfuric acid. Let me just do something different and use sulfuric acid, okay? Any one of these oxygen atoms could conceivably deprotonate, and I don't see a reason why one would be more correct than the other at this point. So just grab one of them, okay? And the focus is, of course, on the aromatic organic chemistry part of the class. So here you're going to form the nitrobenzene, and I won't draw the rest of the products. So you're recognizing that something in solution is going to deprotonate that, okay? So first step, you do these weird two reactions here. You protonate nitric acid, you eliminate water. In the next two steps, you have benzene attacking the nitronium ion, and the last step you have deprotonation by something in solution to make nitrobenzene. Thanks for watching. That's it for this section, and keep on watching the other things for the other reactions. Take it easy.